Well, good morning, everyone, at least those of you who are listening from the West Coast. This is Mikhail Golovnya, Senior Scientist at Salford System, broadcasting from the sunny California. It's a great day here, and I hope that all of you have the same. Now, while they're doing a few of the sound checks here, I just want to make sure that everyone can hear me, and hopefully I'll get that confirmation soon. We're all set? Okay, so I'll continue, and for the next 45 or 50 minutes, we have up to an hour. I'll talk about how one can utilize the power of modern data mining techniques, and most specifically the power of stochastic gradient boosting, which we call TNET and have access to build a better logistic regression models. Now, the topic is of a very high interest, and within that next hour, I'll try to summarize years of experience and also all of the different approaches that we tried. Now, given the constraints on time, I will not be able to cover everything, but hopefully you'll get the flavor of it, and we will follow up this webinar with a set of practical instructions, so should some of you decide to try it for yourself, it will be fairly easy to do. So I will proceed by introducing logistic regression, one of the oldest known classification approaches. The most important thing about logistic regression is that it directly models the probability of the Bernoulli response or the binary outcome. And the key assumption for logistic regression, and again, I'll go a little bit technical here, but then you'll see it's not really that necessary. But the key assumption is that we model log odds of the probability of the event of interest. So in other words, when you have a binary classification model, you're interested in a specific outcome, let's say fraud or response or anything that might be of direct value to your business. In the case of logistic regression, you model the probability of that event of interest. And the way it's modeled internally, from the mathematical definition of it, is instead of modeling probability itself, you focus on the one-to-one transformation called log odds, which is simply the log of a probability of the event divided by the probability of the opposite event. And that's the famous S-shaped curve that is often being talked about in logistic regression. Now, the key assumption behind the logistic regression is that this log odds that you model is a linear combination of available predictors. So if you're trying to model fraud, the probability of fraud, you may have a whole bunch of observed features or variables or predictors. And in the case of logistic regression, you directly model the log odds of that particular event as a linear combination of access. Log odds is unconstrained, therefore it's always nice to work with it as opposed to the probability, which is always has to be between 0 and 1. Anyways, the rest of this is just some mathematics that is not essential here. And let's focus on the key characteristic features of the logistic regression. First of all, one of the advantages, as already mentioned, that it models probability directly. Now, not every classification approach out there models the probability directly. For example, you look at the support vector machines, they usually model the classification structure of things. They do not focus on probability, they rather focus on separating events of one type from events of the other type. If you look at classification trees, same story. They're not explicitly focused on modeling probability, and so on and so forth. Logistic regression has been known for so long, therefore there is all that fancy statistical probability theory available. I myself have a master's degree in computational statistics, and a great deal of that degree was dedicated to statistical inference and all of that stuff. It's easy to build and interpret and can be a very good performer. And I can emphasize this once again. It is well-known fact that logistic regression very often is a very good performer, assuming that you did everything right and supplied the right set of features and also have a nicely representative data set. However, there's also a number of disadvantages, and let us just to mention a few of those in here. The underlying model shape is fixed in advance by the analyst. I mean, I showed it to you before. This is the underlying model shape. The log odds of probability is basically a linear combination of x's. Therefore, if you want to incorporate a concept of interaction, in other words, when one variable changes its influence in the presence of another variable or the values of that other variable, then you will have to do it by hand or rely on some kind of additional considerations. Missing values or records that are incomplete are not easily accommodated within logistic regression, and there are reasons for it, because in the classical approach, the assumption was that you have data set that's nice and clean. More importantly, when you have linearity or when you have data sets that are extremely large and the number of predictors, and it's very easy to get to those data sets in modern day and age, the solution off the box becomes either unstable or even impossible to obtain, and this is where some people attempted to rely on a number of regularization techniques, Bayesian approaches, and things like that. However, what we will do instead, we will rely on modern machine learning algorithms to basically address most, or if not all, of the disadvantages of the logistic regression in order to build the better model. And it looks like pretty much based on all of our past experience that oftentimes this is exactly what you want, because in addition to just building a model, there's all sorts of additional considerations and constraints that you may need to face. So I will introduce one of the techniques that we ourselves find the most useful, at least for our needs. Of course, you may have different opinions, and the rest of the presentation, you'll see that a lot of these ideas that I present here are equally applicable to alternative technologies. But I focus on 3Net, which is also known as GBM, Generalized Boosting Machine, and we'll see how one can use it to enhance conventional logic. Now, in a few words, quickly, 3Net model has quite a number of conceptual similarities to what we already talked about. First of all, it directly models half-log odds of the event of interest. Now, that half is just technicality. The important thing is that whenever you build a 3Net model, the predicted response is basically a direct measure of probability. And the overall model is constructed automatically for you by creating an additive sum of trees. If you're not familiar with trees, and hopefully everyone in this day and age understands the basics of regression tree, but basically any tree is a partition of the data space into a set of mutually exclusive boxes where the rules are usually simple. Only one variable is allowed per individual split point. And within each of those subregions, the predicted response is a constant. So it's a very simple object, but at the same time, it allows us to do the data-driven learning that is not based on any set of individual specific assumptions. As the result of it, important predictors are identified. Nonlinear transformations are automatically included, so you don't have to do them by hand, you don't have to guess them, you don't have to do trial and error. And more importantly, interactions, if necessary, are also automatically accommodated. As the result of all of these advantages, and it could, of course, be a whole other webinar to explain some of the details and some of the features of gradient boosting models, as the result of it is that the model performance can often improve the performance of a painstakingly crafted logistic regression model. So that's the good news. The bad news is that it all comes at a price. You know, like everything in life, sometimes you can get access to something better, but it all comes at a price. And the price in the case of gradient boosting model can be summarized in two important bullet points here. First of all, the scoring code uses a potentially large number of regression trees. The scoring code meaning if you were to take a GBM model and put it somewhere on the server such that it starts generating predicted probabilities for every record. Well, as part of the deployment, you would have to include a large number of nested if-then-else logic that is could become quite cumbersome, especially if you push the limits of modeling and make it very big tree sequences. And number two is that because of the internal structure of the model, and again, I showed it as this sum of individual trees, which could by themselves have reasonable number of if-then-else rules, but there could be hundreds or maybe even thousands of those trees. The end result is that because of that internal structure, you cannot easily describe it by a set of simple parametric equations, and therefore it may not be approved by regulating authorities. Now, those of you who work in banking and finance and elsewhere will know the dreaded words of regulating authorities, and you will also know what it takes to actually approve something that cannot be represented by a set of equations. Such is the price you're paying for potentially superior performance of the model, data-driven, data mining, machine learning approach. Hence, we have the ever-present need to incorporate the insights generated by these powerful approaches back into the conventional framework, which is basically the topic of today's webinar. The good news is that most of the above issues can be successfully addressed using, at this point, I'll focus on tree-net or gradient boosting as basically an example of how it can be linked back into the logistic regression. Here's the suggested procedure, and that summarizes years of our own consulting, and also at some point our clients started using this procedure rather successfully. We first were exposed to gradient boosting back in 2004, and by winning a number of data mining competitions back then, we realized the power of the technique, and then the word kind of spread out, and more people got access to it. And to this day, it's basically one of the top performers out there based on all of the assembled evidence. So the suggested procedure then to incorporate the results of gradient boosting models back into logistic regression is the following. First, you ignore all of the potential difficulties and restrictions mentioned on the previous slide. You basically ignore the regulator, ignore all of those who demand specific model equations, and focus on gradient boosting models to do activity generally known as feature selection. Because models are data-driven, don't rely on any assumptions, and extremely powerful at capturing all sorts of intricacies in your data set, this first item allows you to very quickly conduct powerful feature selection, eliminate all of the redundant features, eliminate features that are not useful or that are not allowed to be used, and quickly narrow down the list down to the essentials. Once you have that first step finished, now comes the time to build your logistic regression and compare performance. Sometimes you will see that the performance of that logistic regression matches the performance of the tree-net or gradient boosting model. Should that happen, you should be happy and basically retire from that particular modeling activity and move to something else. But there will be other situations when the performance of logit will be worse than the tree-net model. And then you have to make a choice. You either decide to make a case for the tree-net model and start using it directly, and it often happens, let's say, if your industry allows it or if the subject area is not very sensitive. Otherwise, you proceed with the next step, which is you try to extract as much information as possible from tree-net GBM model and bring it back into the logistic regression. Now, the very first powerful piece for extraction is transformations. Because tree-net is data-driven, it also has the facility that highlights the essence of nonlinear signals that were captured by all of those internal tree sequences. And as long as you have ways and means to extract those transformations back into some conventional parametric form, and I'll show it in a moment how we do it within our software, the end result is that now we can construct new features that you feed back into the logistic regression model in place of the original features. And by incorporating all of these added transformations, you expect to get a better performance out of this new enhanced logistic regression. And oftentimes, that performance will match the performance of the tree-net model, which would mean mission accomplished as well. Now, in those situations when you still have the residual lack of performance, at this point you usually have no choice but to go after the interaction effects. Now, the interaction effects is the topic that is worthy of the entire webinar in and by itself. It's also somewhat lesser known, and there's a lot of challenges that arise there. But should you decide to pursue it, there are certain ways and means to do it. And in the end, by incorporating insights of that investigation, you can hopefully advance the performance of logistic regression model even further. Again, this summarizes about 7 to 10 years of our own experience of using GBL models, as well as successfully confirmed by many of our clients, names of which we sometimes not even allowed to disclose under an NDA. Okay, so let me illustrate this suggested procedure in real numbers. For that, I'll take 2 real-life examples. I will not work with some artificial examples to highlight this point because it's way too easy. Instead, I picked 2 publicly available data sets. They're all from financial industry, but all of these ideas are equally applicable to all sorts of other situations. The first data set deals with direct marketing and banking, when basically the existing clients are called with an offer to subscribe to a new product, a new term deposit. And the outcome variable is whether they agreed or did not agree to subscribe to that new product. So it's basically direct marketing and banking. A decent-sized data set, especially on the number of instances or observations, and about 12% of cold clients actually responded positively. The second data set is the delinquency prediction in banking, and it's a somewhat modified version of the data set, but it has about 100,000 different clients of some undisclosed bank, and the task is to predict the probability of past 90 days delinquency associated with a given account. Yeah, about 6% of the accounts actually exhibited that type of bad behavior that makes banks really unhappy about. So the first data set, the variables that are presented here, and again, we're interested in modeling whether somebody responded to subscribing to a term deposit. Those are all of the predictors, and again, this is just a small set of what could normally happen in real life, because when you approach those data sets, you will normally encounter hundreds of predictors, maybe even thousands, and sometimes you create all sorts of derived features, and it becomes a challenge in and of itself to even begin working with those things. Now, in my case, I just took that list of 15 predictors and built my first tree-net model based on that list. And the very first thing that happens every time you build a tree-net model, you get the measure of performance of your model in terms of different classification metrics. And you also get to see the list of important predictors ranked according to their contribution. Now, I model direct marketing data set, and whenever I see that the area under ROC curve is 0.92, instead of jumping out from joy, I actually get very worried, because that means that I messed up something and I have used something that I was not allowed to use. Because it's It never happens in real life that when you call someone with that area under ROC of 0.92, they're likely to be happy to respond to your offer. They're much more likely to basically say something unpleasant to you and hang up. But in any case, within seconds, I get to this first model. I see the performance. I look at the list of important predictors, and I see that contact duration is at the top. And that explains what happened. I am basically saying that I can predict that someone is likely to respond by knowing how long, how many minutes I spent on the phone with that person. Now, of course, it's directly correlated with the outcome. The problem is that it's totally useless for my model building activity because I want to know the contact duration before I called someone, and until I called and actually completed the contact, that information is unavailable. Now, a little bit of a silliness to this example, but it highlights things that happen a lot more often than you would normally think. I've seen examples when people spent days, weeks, working out in some logistic regression models only to find out that one of the variables that was at the core of that development was actually a variable that was not allowed to be used. In the case of cleanup, it kind of goes right back to you in your face, and with a few simple clicks, I eliminate that variable and build my next model on the residual and the remaining variables, and now my performance down to 0.76, 0.77, which is a lot more realistic, and now it actually makes me happy. But before I proceed any further, again, I look at the list of important variables, and I can run a whole bunch of experiments by further reducing the number of variables that are in my final model. So for example here, if I focus on the top half of important predictors and rebuild my model again, on the next slide you'll see that I pretty much have almost preserved my model performance, and I reduced the model complexity in half. Again, this is where a lot of particular specifics and judgment will take place. So, for example, you may be perfectly fine with the previous model that gives you an extra half or so point of performance, or you might take this model because it's simpler and easier to deploy. Either way you proceed, there's a lot of flexibility, and you can accomplish all of this fairly quickly with very little mental energy or grunt work, so to say. Now, when you work with data sets, and what I'm illustrating here is the first topic of the suggested procedure, which is ignoring all of the regulatory constraints, just focus on the power of GBM models to do feature selection and highlight things right back, throw them into your face, and make you decide whether you're happy with what you see or not. Now, suppose that at this point, this is the model that makes me happy, and I'm basically finished with this initial feature selection type of activity. And I see that my performance is 0.76. Now I go ahead with the second step and build my logistic regression model using that suggested list of final features. When you build a logistic regression model, again, in our software, it's just a matter of a few clicks. You just say, instead of Peanut Engine, I'll use Logit. Go ahead and build their model, and you'll get to see something like that. Now, first thing that is striking is that performance dropped by about 5 accuracy points, which is huge in terms of area under ROC curve. It could convert into a lot of financial burdens and so on and so forth. What is more important here, when you look at the list of variables, I had a mixture of nominal variables and continuous variables. If you go back to the definition of those 6 that were selected, 3 of them were nominal and 3 were continuous. When you look at the variable called contact day, which encodes basically the day as a 1, 2, 3, 4, whatever within a month, where the contact happened, according to logistic regression, that variable is insignificant. and with all conventional suggestions, it would have to be dropped. And all of the remaining things are pretty much enter as linear combinations. The nominal variables were replaced by individual dummies, and it all happens automatically within, at least within our version of the software. But the end result is unsatisfactory, and now our goal is to try to recover, or at least partially recover, those missing 5 points of accuracy. Now we go back to the tree-net model and open up a powerful facility known as dependence plots. Now, even though internal representation of gradient-boosted models is a linear combination of trees, which totally makes it hidden from you what is really going on and makes it impossible to directly explain the essence of the signal, the dependence plots machinery does a lot of post-processing on that internal complicated model structure and extracts the average suggested transformation of all of the individual predictors as they vary over their range. And again, in the supplement of this webinar, you'll see that at least our software allows very easy superposition of spline approximations to these individual plots. So what you see as the blue curve is the dependency plot generated by tree-net, but the green curve is a simple parametric spline solution that you, as the end user, have imposed on top of each plot. And the whole thing is automated. You can do it within seconds. You can say the suggested number of spline boundaries, click go, and then it does all of those approximations for you automatically. And then you can also enter into interactive mode and do some adjustments on your own. So if you're interested, you can always come back to us for all of those follow-up instructions. And again, notice I only use 3 variables because those were 3 continuous predictors. Categorical predictors might be left as they are because technically there's no great difference other than the interactions component, which we will talk about later, between handling of those in tree-net and, say, logistic regression. So once I've imposed those suggested transformations, and again, as I said, it's very easy to do with the tools that we supply. The end result is that every transformation can be presented as either some built-in basic language, or should you prefer to work with SAS or some other applications like Visual Basic, whatever, you can always switch to a different language of presentation here. The point is that each transformation is simple. You just divide range into different cut points, and in each subset, either first or second order parametric polynomial is built, and the resulting transformation can be presented as some kind of simple parametric code that fits on a single screen. Once you have that code, you can save it such that basically each individual raw continuous predictor can be easily converted into a new form, the transformed form. This is no different than all of these approaches suggested in classical literature to try squares of variables, logs of variables, inverses of variables, S-shaped transformations of variables, and things like that. Here, it's all constructed for you based on the best suggested match between what's extracted by GBM model internally and how it's represented externally. Once you have all of those transformations, you can save them, you can save the code, and you can also ask the software to create those new transformed variables and add them to the output data set. Again, within a few minutes, you can proceed to the next stage, which is rebuilding logistic regression model, but this time using transformed predictors. Now, these _S variables are transformed versions of the original variables when the shape and the definition of each transformation has also been saved for you. And once you do this, all of a sudden you see that you are now recovered pretty much 3 points of the original accuracy loss, which in and by itself could be a very important step forward depending on the goals and the requirements of the project. This performance is way better than the performance of the original logistic regression, and it comes pretty much at no price because you're still using 3 nominal predictors plus 3 continuous predictors, which are based on the univariate transformation of the original continuous predictors, and that's basically a perfectly accepted conventional technique. At this point, I could even forget to mention that I used TreeNet or gradient boosting or any other technique that you may have decided to try in the department, and simply say, look, I've decided based on maybe revelation from above that my predictor previous days has to be transformed like this, and if I use the transformed version, I improved my logistic regression on the test sample by 3 points up. And that is usually more than enough to justify your use of a specific transformation, and you comply with pretty much all of the regulatory constraints. And all of those people who find very uneasy once they get out of the confines or limitations of the conventional logistic regression paradigm. But what about the remaining 2 points? We still didn't manage to recover all of the performance. Well, this is where we have but no choice but to go to that very challenging and difficult domain of hunting down potential interactions. Now, here's the good news. At least within the gradient boosted models, and CNAT in particular, we give you a very simple control over interactions that allows you to either allow or disallow interactions altogether. So if you use that approach, here's what you'll discover. The top part shows performance of my original GBM model with 0.76 area under ROC curve. However, if I rebuild that model and suppress all of the interactions, which is very easy to do, again, it's just one click and then you rebuild your model, all of a sudden the performance drops by 2 points. Now I have basically an independent confirmation why logistic regression model, even after I introduced all of the transformations in the previous step, did not manage to recover the full accuracy on the test sample of the TreeNet model. It has to do with interactions. Those are the remaining missing points. Here's an interesting thing. I deliberately picked this example to share with you is because here it's the very kind of transparent. It does exhibit this characteristic. We've seen it many times in real life situations where at the end of that nonlinear transformation step, you already recover most of the TreeNet performance. And technically, you don't even have to worry about interactions. You don't have to go down this more elaborate and challenging type of activities. But suppose we are in that most challenging situation when interactions are important and you cannot really neglect them. Now, in this case, we know it cost us 2 points of accuracy. Within a GBM model, there is a facility that reports interaction strength, or to be precise, suspected interaction strength for all of the predictors that are part of the model. And again, it would be a whole other topic to delve into details of this. Not everything is as clear and straightforward. There's all sorts of additional considerations that must be accounted for. But at least it gives you something to look at, and with a little bit of trial and error, you can enhance and refine the interaction structure within your GBM model. Like in this case, it was actually pretty straightforward. Based on interaction strength reporting coming out of TreeNet, it was suggested that these 2 variables are topmost interacting ones. And therefore, I went ahead and using some of the parts of the interface that we allow to basically force only those two variables to interact and everyone else to be constrained as additive. And once I rebuilt that model where I imposed a very specific interaction structure, so I basically only allowed interaction for those two variables and everyone else is additive, all of a sudden I pretty much recovered the performance of the original unconstrained model. So combining these two activities, looking at the interaction strength reports and actual rebuilding of models based on those suggested interactions, after a little bit of trial and error, you can reduce the list of suspected interactions down to a much more manageable set. And again, sometimes you may run into difficulties because the signal will not be as strong. But if there's anything that is strongly influencing in terms of interacting structure, the essence of your modeling signal, it will emerge as the result of this activity. And again, once you have that knowledge armed with it, you can try to go back to original logistic regression and try to incorporate some of these effects within that equation and see whether it brings your performance to even higher level. In the interest of time, I'll skip that part, but basically once you have that, contact day and contact month, you would, it's not as simple as just creating a plot because now you have two variables interacting simultaneously, so you'll probably have to bin them or introduce some kind of cross products, because don't forget, one of these variables is actually nominal, the other one is continuous. But with a little bit of extra data prep, you can quickly incorporate that back into the classical logistic regression equation and see whether it was worth it and kind of continue with all of the conventional activities. So let's pause here for a moment and summarize what happened. We took that direct marketing data set and we went through the entire suggested procedure of how to run DBM models to do feature selection. Then we compared it against the conventional logit. Then we used the power of nonlinear transformations to create new features, enhance logistic regression. And then we also focused on the somewhat more challenging area of interaction detection and so on. So that was the entire procedure introduced half an hour ago, actually implemented in a real-life data set. Now, as a statistician, I always feel a little bit uneasy when I'm shown only one example that glorifies the advantages of a certain technique. So I will at least give you a second sampling point, and then hopefully some of you will get interested enough and try it on your own application. So, but let's look at the delinquency data set and follow through that exact same set of steps. Now, we're trying to model the delinquency, and delinquency here is defined as someone who basically was more than 90 days past due in terms of paying their mortgage. And in this case, I skipped that initial part, which is the feature selection, because that is pretty much straightforward in every practical situation out there. You start with a complete list of predictors available, and then you do lots of different runs in order to reduce this list down to the fundamental core, which in this case happens to be 6, just for the example's sake. And now I go ahead and do my second stage, which is compare performance of TreeNet model versus the performance of the logistic regression model built on the same set of core predictors. And just like what we've seen before, it just happens that in this case we have 5-point drop. Of course, in this case, the overall performance into the upper 60s, not the middle 70s, which is not as powerful as in the previous example. But the level of drop in that regard is even more dramatic. Therefore, we do want to see whether we can incorporate parts of the TreeNet back into the logistic regression in order to raise this number all the way up to the acceptable level. And again, the procedure is pretty much the same. This time, all 6 predictors happen to be continuous. And when I open them up in the peanut model, it automatically generates all of those 6 nonlinear transformations. By the way, it's very interesting. It's kind of instructive to look at the shape of those plots. For example, debt ratio, which is basically what is the percentage of your income every month that is being paid, that you have to basically pay to your debt. And the debt ratio in this case happens to be dependent like this. And now you notice as it goes, as it's below 30%, you are within this relatively flat area of dependency. And then once it goes up into 2/3 and so on, there's this rising trend, and there's a real rising trend as it approaches towards 1.0, because some of these accounts were actually business users, not necessarily individual households. More interestingly, the number of open lines. The dependency here exhibits the nonlinear shape. And the number of open lines is basically how many different lines of credit you currently have. Now, you may have no currently open credit lines whatsoever. Let's say if just a newcomer to this country, the way I was about 20 years ago, and had a heck of a hard time getting my first credit card account open. Or you could have a lot of open lines. Let's say you have a mortgage, you have a car, you have another home equity loan, then you have credit cards. So this number of open lines includes every different open sources of debt that you have. And it turns out that as soon as you hit 4, you have this sweet spot. Because remember, we're modeling contribution into half-log odds of delinquency. If what this curve here tells us is that once you reach about 5 or 6, you're in the sweet spot, at least from the banking point of view and as evidenced by the data that we have. Of course, things could change in the future, but at least based on the evidence available in our data set at this specific historical point in time, this is what happens. So once you hit that point, you're fine. But as you go into higher levels, there may be some rising trend or some fluctuation here and there. Likewise, age. It turns out that the riskiest segment is 25 years old. Now, that's because it has this highest bump there. And the best segment is the retirees, because they are much more likely to keep on their monthly payments, and hopefully nothing will happen to their health as they do that or anything. But it's the kind of striking example of how CNET captures the dependency and the quick kind of improvement in terms of delinquency. Same thing with monthly income. The riskiest segment is those who are about $2,500 a month, but then it kind of improves. But what's even more important is very interesting that it's also improving as you go towards having no income. And my explanation is, and again, it's just a conjecture, but for lack of a better thing, I would say if you have no income and you're already paying off some kind of mortgage, it's not you who's paying, it's probably your parents or someone who is a lot more trustworthy than you. In any case, those are all these localized insights that GPM models throw back at you very quickly. And now by imposing these transformations, I proceed by exporting them into new transformed variables. And if I now rebuild a logistic regression model, all of a sudden, I recovered the performance of the original CNET model almost to the last point. And again, I use 6 transformed predictors in this case. And the transformations are represented by a simple transforming code that was saved and preserved. And I recovered my performance, which means that I'm done. I don't even have to worry about interactions. at this point. Just because I already covered the performance of the original peanut model using logistic regression model that incorporated no interactions, that in and of itself already proves that at this point my efforts can be completed. And that's, again, a very good illustration of what may happen in real life. And I did not include the third example that it may happen, if I go back here, that once you build your peanut model and compare it against the logistic regression model, you may see very little performance change. Now that would be the evidence that whatever is present with a signal structure in your data set is so simple that you do not have to go into the areas of nonlinear transformations and interactions. In fact, sometimes it happens with increased numbers of variables and predictors, and it's just because when you increase the number of dimensions, sometimes nonlinearities associated with low dimensions are kind of expanded out into linearities in the higher dimensions. Now, that statement might sound a little bit cryptic to some of you, but it just happens that the entire machinery of support vector machines, SVMs, is centered around this observation. Now, they push it to the extreme, meaning that sometimes they do the expansion into infinite dimensionality spaces, but they try to exploit it in the kind of the most natural way. So that may happen, that when you have a lot of predictors, when you compare TNet versus logistic regression, then they will be quite comparable. However, once you reduce the number of predictors down to the ones that are shown as being most important and all of that, oftentimes you will get to see the difference. And that's where this trick of running transformations and rebuilding your logistic regression models in transformed sets of predictors will prove to be very fruitful. And again, the reason why using a large number of predictors is oftentimes frowned upon is that those models, even when they are cast in the conventional logic paradigm, could still be quite unwieldy. You can have long run times to build those models. You can introduce all sorts of instabilities. Some coefficients might end up being not significant. And you still need to go through some really kind of difficult contortions trying to present that model, because it's one thing to present a model that has a handful of predictors, albeit somewhat transformed, so coupled with these transformation schemes. And it's a whole other matter to try to present a model that has 300, 400, 500 binary indicators in some kind of intricate structure that happens to recover the performance or nearly recover the performance of this simpler model. So in a way, this channel that I'm showing to you here allows a lot more flexibility and the freedom of choice. So to say, you're not constrained by some artificial structural confines and constraints of the conventional classical techniques. So what have we learned? To summarize it, I have shown two real-life examples to illustrate how the powerful facilities of TNet GBM models can be used to craft better performing logistic regression models. And the first thing, of course, is feature selection, and which allows you quickly to focus your attention on the set of predictors that are truly important, and also eliminate the ones that you wish you could use but you simply can't. The second part is the dependency plots machinery. It gives you ways and means to automatically discover meaningful transformations of variables. So you short-circuit a lot of the trial and error that usually goes into conventional modeling technique when you are forced to try a large number of different transformations. So instead of trying something out of the blue, you're actually guided by GBM output to decide what are transformations to consider. And third, when you have interaction controls and reporting coupled with some reasonable amount of trial and error, you can extend the performance of your models even further should it become necessary, because oftentimes it will not come down to that step altogether, as you've seen in the second example above. But should you decide to pursue this particular topic, there are still ways and means to address it, and the end result will be perhaps in even better quality models, while still within the natural confines and assumptions of the conventional logistic regression with all of the advantages therefore. And that's basically one of the key elements and key advantages of all of the suggested procedures here. So hopefully that gives you enough of a flavor of what can be done. And as I have said, this is not something that is presented on truly abstract forms. It has been used many times over in real life for those who are in the know. It's been used by us. It's been used by our clients. And hopefully at this point, when somebody tells you that, oh, GBM models are great, but it's impossible to explain them or to use them or to pass them by the regulator, now you'll know the answer, that nothing could be further from the truth. Now, the trick is, instead of trying to pass the model itself, is to leverage the dependency plots and interactions to extract all of the useful knowledge from that model and bring it back within the conventional paradigm. And again, I use the software that we developed just because I mean, it's available to us, and hopefully some of you will have access to it. And it makes a lot of these things very easy and straightforward to do. But you're welcome to try the same set of ideas using anything else, because the ideas themselves are universal, and they mark the difference between classical parametric models versus modern nonlinear data-driven techniques. In the end, we're hoping to increase the performance of our classical models by incorporating two elements, nonlinear transformations and interactions. Now, in the old days, you will have to do it by hand. You will have to do a lot of brainstorming and decide what seems reasonable and give it a try, see if it worked, and see if it gave you what you wanted. And even today, that's often actually a very fruitful approach, because nothing can replace the power of the domain expert. Someone who spent years working out, say, these logistic regression models, who knows the behavioral aspects of the subject area. And I mean, that is irreplaceable. I mean, you can't just replace it with some dumb machine that, instead of the brain, has some superheated CPU running on billions of cycles per second. I mean, that's still not going to replace your expertise. However, it can help you enormously to short-circuit all of these things that otherwise you will be wasting your time on. And should it be acceptable to use the nonlinear models without the simplifications that I showed as part of this little webinar, you can actually use the fruits and the results of those types of techniques. So in the end, to summarize it, it's always nice to have access to all these recent developments in machine learning and data mining and data science. And as long as you understand all of the key benefits and learn how to use them to bring them back within whatever confines and restrictions that you may have, either historically or environmentally, you will be able to advance your own career, your benefit, and your model building experience. And hopefully the little webinar has convinced some of you on the real benefits of doing this types of activities. So with that, I'm going to end. If you have questions, feel free to send those questions to us. It may take us a few days to address them, depending on the level of complexity. I know there's been quite a few people attending, which is why it's not like questions and answers sessions that we sometimes make. We will also try to come up with a follow-up package that basically gives you a set of instructions that you can go through with the use of auto software in these data sets to basically reconstruct or nearly reconstruct pretty much everything that I have done. Because the part where there's a little bit of ambiguity is when you create those transformations, because some of it is basically your own judgmental decisions, like how many knots, how many types of transformations, so you may have slightly different results. But by and large, you will pretty much get access to a very simple set of steps that replicate everything that I have done. And again, it took me, I could go through the entire process in the software on both of these two data sets within probably 15 or 20 minutes of time. And therefore, once we get that package for you, you should be able to do the same. We're also about to release the next version of software, SBM 8.0, and that's the version that I've been using rather successfully in my work, and it incorporates a lot of these ideas that I presented here in an even more straightforward and natural way. With that good note, I just welcome all of you to this wonderful world of non-linear modern data mining, machine learning techniques, and I hope that all of you will have a great rest of the day and a lot of excitement in your careers. This is Mikhail Golubny, Senior Scientist at Salford Systems, and you're welcome to send your questions to us, and we're looking forward into future cooperation. Thank you very much, and I'll be out.